Welcome to a new episode of the podcast. Vox Agent is made by AI for business executives that work with AI. Today we're diving into a concept that is really shaking the very foundations of deep learning architecture, something called nested learning, or NL. For decades, the thinking has been pretty simple. If you want a smarter model, you just stack more layers, make it deeper. But our source material today, it's this kind of conceptual manifesto from some leading researchers, and it just fundamentally challenges that whole idea. It suggests that just piling on depth can give you what it calls an illusion of deep learning architectures.
That's a really critical place to start. The illusion, right. The argument is that we've been, obsessed with architectural scale when we should have been focused on architectural sophistication. So our mission today is to unpack this whole conceptual framework. We need to explain exactly how it solves these huge persistent problems like catastrophic forgetting in LLMs. And most importantly for you, we want to translate what this means for actually deploying AI in an enterprise setting. We're talking costs, interpretability, the whole nine yards.
Okay, let's get into it. This central idea, the illusion of depth. The premise is that our current methods learn by compressing their own context flow, so they're already kind of implicitly nested. But when you just stack more and more identical layers, you eventually hit a wall. Why is that? Why isn't deeper always better?
It really boils down to a couple of classic problems: parameter coupling and vanishing gradients. In a big monolithic model like a transformer, everything's trained on a single clock. All the layers are so tightly connected. And to make that stable, the network often just defaults to simpler solutions. You might have billions of parameters, but the effective learning capacity doesn't actually scale with that number. So it's structurally deep, but functionally it's shallow. And that's the illusion.
And that leads right into the crisis that NEL is supposedly designed to fix. The fact that once these huge LLMs are pre-trained, they're static, they're done.
Exactly. They're brilliant at what they learn, but they can't continually learn new things after you deploy them, not without a massive disruptive retraining process.
The sources use this incredible analogy. They say these models suffer from something like interrograde amnesia.
It's such a powerful way to frame it. I mean, think about the famous case of patient HM after his surgery. He could remember everything from his past his whole life before the operation, but he completely lost the ability to form new long-term memories.
That's a perfect parallel. An LLM's context window is its short-term memory, right? And its pre-trained weights are its long-past memory. But there's nothing in between. New information from the context window never makes it into those deep foundational parameters, so it can't learn on the job.
And this is where we get to the neurophysiological inspiration behind nested learning. If the current design leads to amnesia, we have to look at how the brain avoids it. And the brain uses two key things: neuroplasticity, the ability to physically rewire itself, and crucially, multi-timescale updates.
Right. That feels like the real aha moment here.
Yeah.
Memory in the brain isn't just one single event. You have this rapid, what they call online consolidation for immediate stuff, and then a much slower offline consolidation, which is like reorganizing memory while you sleep.
And that's possible because the brain doesn't have one central clock. Different parts update at totally different frequencies. We can actually see this in brain waves. You have the high-frequency neurons like gamma and beta waves for active thinking. And then you have these much slower waves like alpha, theta, and delta that are linked to memory consolidation and deeper states of rest.
So NAL just borrows that idea directly. It ditches the single synchronous clock.
It does. Each level in the NL architecture gets its own update frequency, mirroring those biological timescales. You can think of it like this. The fastest gamma waves correspond to the highest frequency parameters in the model, the ones dealing with the immediate context, and the slowest delta waves, that's like the slowest layer in the model, responsible for storing world knowledge, things that shouldn't change quickly. This separation is key to avoiding that catastrophic forgetting.
Okay, so that's the why. Let's talk about the how. NL moves away from just stacking layers and starts representing a model as this system of nested multi-level optimization problems.
It's a great way to put it. The model is sort of learning how to learn over these different time horizons. And it views everything, the networks, the optimizers, all of it, as what it calls associative memory systems. So in this framework, memory is a neural update, and learning is just the process of acquiring effective memory.
Can you walk us through that concrete example again? The one that shows how this nested structure is actually already hidden in the tools we use every day.
Yes, this is probably the most important concept to grasp. So imagine you're training a very simple one-layer network with standard gradient descent. That's a one-level associative memory.
Simple input, simple update.
Right. But now You switch to using gradient descent with momentum, which, basically everyone does.
It's standard practice, yeah.
All of a sudden, the system becomes a two-level optimization process. The network weights are the outer loop trying to solve the main problem.
And the inner loop is?
The momentum term itself, it's its own associative memory. It compresses the history of past gradients. It remembers the direction it was going. So the outer loop uses that accumulated knowledge from the inner loop, the momentum, to make a smarter update. NL just says, hey, this structure is already here, hidden in our optimizers. Let's make it explicit and build on it.
I have to stop you there, though. We've seen ideas like hypernetworks or MML, model-agnostic meta-learning. They're all about learning to learn.
Yeah.
How is this fundamentally different? Is it just a new name?
That's a really important question, especially if you're assessing risk. So things like MML, they usually focus on optimizing initial parameters before you deploy the model. They're a form of explicit meta-learning. NL is different. It's about structural and online learning. The learning algorithm itself is a component inside the system, allowing it to self-modify during deployment. It's built for continuous operation across multiple timescales, which those earlier methods weren't really designed for.
That makes sense. It's about building dynamic, self-tuning organs, not just finding a better starting point. So what are the new building blocks for this hierarchy?
The main one is called the Neural Learning Module, or NLM. You can think of it as a self-contained little unit. Each NLM has an inner model for the task and an outer model, which is its own learning algorithm, its self-update rule. And you can nest them, so a higher-level NLM can actually control how a lower-level one learns.
And to solve the amnesia problem, to actually store new long-term facts, they use that dynamic memory system.
Yes, that's the Continuum Memory System, or CMS. It's a chain of MLP blocks. But the crucial part is that each block in the chain is tied to a progressively slower update frequency. So it gets rid of the binary short-term versus long-term memory idea. Instead, information solidifies across a whole continuum of timescales.
Which brings us to the actual architecture they built to test this. HOPE. This is where the theory gets put into practice.
Right. HOPE is the validation. The research shows that a standard transformer is basically a special single-level case of NL where the feed-forward network, the part that stores the knowledge updates, well, almost never. Its frequency is basically 0 after pre-training. It's a static library.
So the transformer is a static architecture that just looks dynamic during inference. HOPE is designed to be dynamic from the ground up.
Exactly. HOPE breaks that static model by using multiple feed-forward networks. It has a high-frequency FFN, a mid-frequency one, and a low-frequency one. The high-frequency one handles rapid changes in the context. The mid-frequency handles, say, episodic memory over a conversation. And the low-frequency one is where the really stable long-term knowledge gets consolidated.
So by separating the update speeds, new information doesn't just wipe out the old facts.
Precisely. And this isn't just theory. The performance numbers are really compelling. On the Wiki Language Modeling benchmark, the 1.3 billion parameter HOPE P model got a perplexity score of 15.11.
That's a huge deal. And for our listeners, perplexity is just a measure of how surprised a model is by the next word. Lower is better.
It's a very significant improvement. You compare that 15.11 to a 1.3 billion parameter transformer plus law, which scored 18.53. That's not a small gap. That's a real quantifiable gain that comes directly from this architectural shift. It also beat other modern architectures like RetNet, proving that this kind of sophistication can be more powerful than just adding more parameters.
Okay, let's pivot this to the boardroom. We get the technical side. But how does this translate into actual strategic value for someone deploying AI in their business?
I'd say the value is twofold. First is efficiency. These NL models get state-of-the-art results with way fewer parameters. That means lower operational costs for training and inference. And critically, this efficiency means you can deploy these models on resource-constrained edge devices. Think sensors on a factory floor or in remote field equipment.
And why is it better for the edge than just using a smaller transformer?
Because of the modularity. You don't have to retrain the whole model when local conditions change. You can just update the high-frequency NLM on the device itself. That saves a massive amount of power and bandwidth, and it allows for continuous local adaptation in a way that just wasn't feasible before.
Okay, so efficiency is one, and the second was system resilience, which I imagine connects back to the messiness of real-world enterprise data.
It does. NL naturally fits with the kind of hierarchical data you see in business org charts, nested transaction histories, supply chains. And this improves not just performance, but also interpretability. You get what we can call modular accountability.
Now, that is a huge point for anyone in a regulated industry.
Absolutely. Instead of just a black box said so answer, If a prediction is wrong, you can actually trace it back to the specific NLM that made the call. You can see if the error came from the subnetwork processing inventory data versus the one processing sales data. It allows for much more targeted auditing and debugging.
Can you walk us through one of those use cases? Let's take manufacturing. How would this multi-scale approach actually work?
Of course. Predictive maintenance is a perfect fit. You could have an inner NLM, a high-frequency one, that does nothing but monitor vibration data from a specific machine bearing, updating every second. Then you'd have an outer, slower NLM that only looks at data once a day. Things like the overall engine temperature or reports from oil analysis.
So the fast NLM spots the immediate problem, and the slow NLM understands the long-term health trend.
Exactly, and they work together. The system can make incredibly optimized maintenance decisions because it's processing information across all the relevant timescales at once. It can prevent downtime in a much more sophisticated way.
And what about something like cybersecurity?
Another great example. Traditional systems look at events in isolation. NL models can see the entire attack chain as a nested sequence. A low-frequency NLM builds a long-term model of what's normal for an employee. A single failed login flagged by a high-frequency NLM is probably just noise. But if that login is followed by unusual database queries and then a large data transfer, all of which violate that long-term normal pattern, the system can flag it as a sophisticated, coordinated attack that isolated analysis would totally miss.
And in healthcare, I imagine analyzing data at different resolutions is key.
For sure. Take a disease like Alzheimer's. You need to analyze cellular-level data, like plaque formations, at the same time as tissue-level data, like atrophy, and even system-level data, like cortical thinning over many years. An NL model can integrate all those different scales simultaneously, leading to much more accurate and reliable diagnostics.
This sounds incredibly powerful. It also sounds incredibly complex to manage. This isn't a silver bullet, right?
Yeah.
What are the biggest hurdles to adoption?
Complexity is definitely the #1 barrier. First, there's the technical complexity. Designing and debugging these non-linear hierarchical models is not a trivial task. It creates a huge skills gap. You can't just have your existing ML engineers pick this up over a weekend. You need people who really understand these deep meta-optimization concepts.
And what about the tools? Our MLOps pipelines are all built for linear models.
You've hit on the second major problem, the MLOps hurdles. The entire infrastructure we've built for deployment, versioning, monitoring, it's all designed for stable, monolithic models. Managing a system where different parts update at different speeds requires a fundamental re-engineering of those pipelines. It's a serious infrastructure investment. So to sort of sum it all up, the key takeaway here is that nested learning is a strategic shift. It's moving away from brute force scale, just making things bigger, towards architectural sophistication and true self-adaptation. It's a long-term investment, but it offers a path to building AI that is much more resilient and can actually learn continuously.
And that leaves a really fascinating question for you, the listener, to think about. If the whole design of today's LLMs has been based on this illusion of depth, what complex hierarchical problems in your own organization are you failing to solve right now? What challenges in your supply chain or in your risk modeling are you just unable to tackle because your AI architecture can't handle the system's complexity of the real world? Thank you for joining the podcast, and see you soon.